When installing a new 4000 amp main with a ground fault circuit interrupter, GFCI at a business with a 277/480 volt system, the existing lighting panel configuration needs careful consideration. The new GFCI main breaker will monitor the differential current between the line and neutral conductors on all circuits, including the lighting circuit. If the existing lighting is supplied using one line and a neutral, creating a 277 volt circuit from a breaker to a subpanel, simply connecting this to the new main with the GFCI protection could lead to unintended tripping. If there is a fault on the lighting circuit, any current leakage to ground will be detected by the GFCI main, causing it to trip and interrupt the power supply. This is its intended function, preventing electrical shock hazards. Therefore, modifications to the lighting panel are required to ensure it is properly wired for the GFCI main to effectively monitor current. Upgrading the lighting panel to a type that supports GFCI protection is essential. This may involve installing a GFCI circuit breaker directly within the lighting panel, or alternatively, installing a separate GFCI device within the panel to provide the necessary ground fault protection for the lighting circuits. It is generally not necessary to install a transformer to feed the lighting panel in this scenario. The GFCI main will still function correctly to monitor the lighting circuit, even if it operates at 277 volts. The GFCI main operates by measuring the differential current, which is the difference between the current flowing in the line and neutral conductors. The voltage level of the circuit does not affect this measurement. The critical factor is the imbalance between the line and neutral currents, which indicates the leakage of current to ground. To ensure successful and safe installation, several steps should be taken. Firstly, consult the manufacturer's instructions for both the GFCI main and the lighting panel. These instructions will provide specific installation requirements and guidelines tailored to the equipment being used. Secondly, and most importantly, it is highly recommended to hire a qualified electrician to perform the work. A qualified electrician possesses the knowledge, skills, and experience necessary to safely and correctly install the GFCI main and modify the lighting panel. They can also verify the proper functioning of the GFCI protection after installation. Ground fault circuit interrupters, GFCIs, are designed to protect people from electrical shock. They do this by monitoring the current flowing in a circuit. If there is a difference of more than a few milliamperes between the current flowing into the circuit and the current flowing out of the circuit, the GFCI will trip the circuit, cutting off the power. This difference in current indicates that some of the current is leaking to ground, which could be through a person's body. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor outlets. They are also often used in industrial settings to protect workers from electrical hazards. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. It is also important to test the GFCI regularly to make sure that it is working properly. To test the GFCI, you can press the test button on the GFCI. This should trip the circuit. If the circuit does not trip, the GFCI is not working properly and needs to be replaced. In the context of a 277/480 volts electrical system, understanding the implications of using a GFCI main breaker with existing 277 volts lighting circuits is crucial. The National Electrical Code (NEC) provides guidelines and requirements for electrical installations, including GFCI protection. The NEC specifies where GFCI protection is required, and it also provides guidance on how to install GFCIs properly. It's important to consult the latest version of the NEC and local electrical codes to ensure compliance. In industrial settings, 277 volts lighting is common due to its efficiency over long distances. However, introducing a GFCI main breaker into such a system requires a careful assessment of the existing wiring and equipment. The primary concern is ensuring that the GFCI breaker doesn't nuisance trip due to normal leakage currents in the lighting circuits. All electrical equipment has some level of leakage current, and a GFCI breaker is designed to trip when this leakage exceeds a certain threshold, typically 5 milliamperes. If the cumulative leakage current from the lighting circuits exceeds this threshold, the GFCI breaker will trip, even if there is no actual ground fault. To prevent nuisance tripping, the lighting circuits may need to be reconfigured or upgraded. One option is to install individual GFCI breakers at each lighting circuit. This would isolate any ground faults to a single circuit, preventing the main GFCI breaker from tripping. Another option is to use lighting fixtures and ballasts that are designed to minimize leakage current. These fixtures typically have better insulation and grounding, which reduces the amount of current that can leak to ground. Another point is the selection of the appropriate GFCI breaker. GFCI breakers are available in different trip current ratings. The appropriate rating for a particular application depends on the amount of leakage current that is expected in the circuit. In general, it is best to use a GFCI breaker with the lowest trip current rating that is practical. This will provide the best protection against electrical shock. Furthermore, proper grounding is essential for the safe and reliable operation of a GFCI system. All electrical equipment must be properly grounded to provide a path for fault current to flow back to the source. This path allows the GFCI breaker to quickly detect a ground fault and trip the circuit. Grounding should comply with NEC Article 250. The equipment grounding conductor should be sized according to NEC Table 250.122 based on the overcurrent protective device rating. Additionally, the grounding electrode system should be installed per NEC Article 250 Part 3, which includes requirements for grounding electrodes such as ground rods, ground rings, and metal water pipes. In addition to the technical aspects, safety is paramount when working with electrical systems. Before working on any electrical equipment, it is important to energize the circuit. This can be done by turning off the circuit breaker or removing the fuse. Once the circuit is energized, it is important to verify that it is actually dead using a voltage tester. Never assume that a circuit is energized simply because the breaker is off. Also, wear appropriate personal protective equipment (PPE) such as safety glasses, gloves, and insulated tools. Working with electricity can be dangerous, and it is important to take all necessary precautions to prevent injury. Consider the situation where there is an existing lighting panel fed with 277 volts, derived from a 480 volt system, and the introduction of a new GFCI main breaker. In this scenario, the existing lighting panel is likely configured with a two-wire system consisting of a hot wire and a neutral wire. When a GFCI breaker is installed, it monitors the current balance between the hot and neutral wires. If there's any imbalance indicating current leakage to ground, the GFCI trips to interrupt the circuit. The challenge lies in the fact that older lighting systems might have inherent leakage current due to aging insulation or improper grounding. This leakage, even if not a hazardous fault, can trigger nuisance tripping of the GFCI breaker. One approach to mitigate this is to ensure the lighting panel and associated circuits meet current electrical code standards. This involves verifying proper grounding of the panel and all lighting fixtures, replacing any damaged or deteriorated wiring, and ensuring all connections are tight and corrosion-free. The grounding system should be thoroughly inspected to ensure it meets the requirements of NEC Article 250, which covers grounding and bonding. This includes checking the grounding electrode conductor size, the grounding electrode system, and the bonding of all metal parts. Additionally, consider using lighting fixtures and ballasts that are specifically designed to minimize leakage current. These products often incorporate improved insulation and grounding features, which can significantly reduce the risk of GFCI tripping. Another factor to consider is the sensitivity of the GFCI breaker itself. GFCI breakers are available with different trip thresholds, typically ranging from 5 mA to 30 mA. A more sensitive GFCI breaker e.g. 5 mA will provide greater protection against electrical shock, but is also more prone to nuisance tripping. A less sensitive GFCI breaker e.g. 30 mA is less likely to nuisance trip but offers less protection. The appropriate trip threshold depends on the specific application and the level of risk involved. In some cases, it may be necessary to install a separate isolation transformer to feed the lighting panel. An isolation transformer provides a separate, isolated power source for the lighting circuits, which can help to reduce leakage current and prevent GFCI tripping. However, this is typically only necessary in situations where the existing lighting system is very old or has significant leakage current problems. When working with electrical systems, it's always best to consult with a qualified electrician who can assess the specific situation and recommend the most appropriate solution. They can perform a thorough inspection of the existing wiring and equipment, identify any potential problems, and ensure that all work is done safely and in accordance with electrical codes. Remember, electrical work can be dangerous, and it's always best to leave it to the professionals. In addition to the technical considerations, it is also important to consider the economic aspects of GFCI protection. GFCI breakers and receptacles are more expensive than standard breakers and receptacles. However, the cost of GFCI protection is well worth it in terms of the safety it provides. The cost of an electrical shock can be significant, both in terms of medical expenses and lost productivity. In some cases, an electrical shock can even be fatal. GFCI protection can help to prevent these types of accidents. The NEC requires GFCI protection in many locations such as bathrooms, kitchens, and outdoor outlets. However, even in locations where GFCI protection is not required by code, it is often a good idea to install it. GFCI protection is a relatively inexpensive way to improve the safety of an electrical system. When selecting a GFCI breaker or receptacle, it is important to choose a product that is listed by a recognized testing laboratory, such as Underwriters Laboratories UL. This listing indicates that the product has been tested and meets certain safety standards. It is also important to choose a product that is appropriate for the intended application. For example, GFCI receptacles that are used outdoors should be weather resistant. Installing a GFCI main breaker in a 277/480 volt system with existing 277 volts lighting requires careful consideration of several factors to ensure safety and prevent nuisance tripping. Firstly, assess the existing lighting system for any potential sources of leakage current, such as old or damaged wiring, improper grounding, or incompatible ballasts. Secondly, ensure that the lighting panel and all connected circuits meet current electrical code requirements, including proper grounding and bonding. Thirdly, consider using lighting fixtures and ballasts that are designed to minimize leakage current. Fourthly, select a GFCI breaker with an appropriate trip threshold for the application. Fifthly, in some cases, it may be necessary to install a separate isolation transformer to feed the lighting panel. Finally, always consult with a qualified electrician who can assess the specific situation and recommend the most appropriate solution. One crucial aspect often overlooked is the cumulative effect of leakage current. While individual lighting fixtures may have minimal leakage, the combined leakage of numerous fixtures connected to the same circuit can exceed the GFCI trip threshold. This is particularly relevant in large commercial or industrial settings with extensive 277 volts lighting systems. To address this, consider dividing the lighting load into multiple circuits, each protected by its own GFCI breaker. This reduces the number of fixtures per circuit, thereby minimizing the cumulative leakage current. Another strategy is to use line filters or surge protection devices specifically designed to reduce leakage current. These devices can be installed at the lighting panel or at individual fixtures to filter out unwanted noise and leakage components. Furthermore, regular maintenance and inspection of the lighting system are essential to prevent leakage current from increasing over time. This includes checking for loose connections, damaged wiring, and corroded components. Any issues identified should be promptly addressed to ensure the continued safety and reliability of the system. The type of wiring method used can also impact leakage current. For example, metallic conduit provides better shielding and grounding compared to non-metallic conduit, which can help to reduce leakage current. Similarly, the use of shielded cables can minimize electromagnetic interference and leakage. It is also important to ensure that all metal parts of the lighting system, including fixtures, conduits, and junction boxes, are properly bonded together. This creates a low impedance path for fault current to flow back to the source, which is essential for the proper operation of the GFCI breaker. The bonding should comply with NEC Article 250 Part 5. In summary, installing a GFCI main breaker in a 277/480 volt system with existing 277 volts lighting requires a comprehensive approach that considers all potential sources of leakage current, code compliance, equipment selection, and system maintenance. Consulting with a qualified electrician is highly recommended to ensure a safe and reliable installation. Remember that the primary goal of GFCI protection is to prevent electrical shock and save lives. While nuisance tripping can be inconvenient, it is always better to err on the side of safety. If the GFCI breaker trips frequently, it is important to investigate the cause and address the underlying problem rather than simply disabling the GFCI protection. Furthermore, consider the use of arc fault circuit interrupters (ASIs) in addition to GFCIs. ASIs protect against arc faults, which are another common cause of electrical fires. ASIs detect the unique characteristics of arc faults and trip the circuit to prevent a fire from starting. The NEC requires ASIs in many locations, such as bedrooms and living rooms. In conclusion, when installing a GFCI main breaker in a 277/480 volt system with existing 277 volt lighting, prioritize safety, code compliance, and proper equipment selection. A comprehensive assessment of the existing system, coupled with regular maintenance and inspection, will ensure a reliable and safe electrical installation.